This is Dr. Brown. In this video we're going to talk about the derivative of trig functions. And we're going to start off by doing a little intuitive thinking. Here is a graph of the sine function, and we're going to look at this graph and see if we can discern what the slope of the tangent line it would be at various points on the sine function. The first thing we would notice here is that at pi over 2 it's got a zero slope tangent line, so we would believe that the derivative of sine of x at pi over 2 would be 0. Similarly, you would say at minus 3 pi, at plus 3 pi over 2, the derivative would be 0. At minus pi over 2, the tangent line looks like the slope would be 0. And then at minus 3 pi over 2, the slope of the tangent line would be 0 also. So we have 1, 2, 3, 4 places on this graph that the slope of the sine wave would be 0. And then let's look at x equals 0. If you draw a tangent line at x equals 0, and also remember that sine of x approaches x as x approaches 0. So sine x and x look pretty much the same and approach one another around x getting closer to 0. The slope of the straight line y equal x is just 1. So we would believe that the derivative of the sine function at x equals 0 would be 1. Similarly, looking at x equal 2 pi, the slope looks the same as it does around x equals 0, and so we believe the derivative would be 1 there. At minus 2 pi, we believe the derivative would be 1 there. And then looking at pi and minus pi, it appears that the slope would be the same at x equals 0, except it would be negative. So we believe the derivative of the sine of x at x equal pi would be minus 1. So we'll put a dot down here at minus 1. Similarly, at minus pi, we would put minus 1 as the derivative. And now trying to put together a graph of this, we might believe that the slope would look sort of like this. I'm not a perfect artist, but it would look something like this. And now we have a graph that looks pretty much like we believe the derivative of the sine function would look. And notice that this is a graph of cosine of x. Sine and cosine, as you know, have the same graph, except they are phase shift by 90 degrees or pi over 2. So the first thing we believe is that the derivative of the sine function is equal to cosine of x. And we'll prove this in just a moment. Now let's look at the cosine function. First of all, at x equals 0, it looks like the cosine function has a derivative of 0, zero slope tangent line. At pi over 2, the slope looks like it would be minus 1, so we put in a point minus 1 at pi over 2. We put 0 in at pi. The derivative of the cosine function at 3 pi over 2 looks like it would be 1. And then at 2 pi, it's going to be 0 again. At minus pi over 2, looks like it's going to be 1. At minus pi, it's going to be 0. And at minus 3 pi over 2, it looks like it's going to be minus 1. And at minus 2 pi, it looks like it's going to be 0. So now we can plot a curve connecting these points that we believe we have accurately calculated the derivative for. And this is what we come up with. Notice this looks exactly like the sine wave, except it's minus sine wave. So we believe that y prime equal d dx of cosine of x is equal to minus sine of x. So our conclusion here is that the derivative of cosine of x is a negative sine of x. Now let's do a formal proof of the derivative of the sine function. The formal proof of the derivative of the cosine function is very similar, so we'll just do the one for sine here. You will recall in trig that sine of a plus b was one of the identities that you studied. Sine of a plus b would be equal to sine of a cosine of b plus cosine of b sine of a. Now, to find the derivative of a function, we have to take f of x plus h minus f of x divided by h and find the limit as h approaches 0. Well, that would entail finding sine of x plus h minus sine of x divided by h. So that is why we use the sum formula here. Sine of x plus h would be sine of x cosine of h plus cosine of x sine of h. Plugging this in to the formula, we now get that the derivative is the limit as h approaches 0 of sine of x cosine of h plus cosine of x sine of h minus sine of x. And the next thing that we do is notice that we have a sine of x here and a sine of x here, and so we now regroup some of these terms, factor out the sine of x, and we have that times cosine of h minus 1. And then we place the cosine of x sine of h in this position, all divided by h. And we now can take the limit as h approaches 0 of this portion plus the limit as h approaches 0 of this portion. Notice that sine of x does not contain an h, so we can factor sine of x out and have the limit as h approaches 0 of cosine of h minus 1 divided by h. Cosine of x has no h in it, so we factor that out and have the limit as h approaches 0 of sine of h over h. Now, if you look in section 2.4 of the textbook, example 5a, you'll see that this limit is 0. And of course you remember that the limit of sine of h over h as h approaches 0 is equal to 1. So now the entire problem reduces to the fact that the derivative of f is equal to cosine of x plus 1, which is cosine of x. So that proves that the derivative of sine of x is cosine of x. And you can also look at the textbook for the derivative of cosine of x, and I'll just simply repeat it here. d dx of cosine of x is equal to minus sine of x. Now we can work several problems here that involve polynomials and sine functions and exponentials. The first example is the derivative of x squared minus sine of x. Taking the derivative of each portion separately, the derivative of x squared is 2x. The derivative of sine of x is cosine of x, so this whole thing would be minus cosine of x. Now, to find the derivative of e to the x times sine of x, we'll use the product rule. So that would be the first times the derivative of the second, which would be the derivative of sine of x, plus the second, which is sine of x, times the derivative of the first, which is derivative of e to the x. The derivative of sine of x is cosine of x, so we get e to the x cosine of x. The derivative of e to the x is e to the x, so we get e to the x times sine of x. And finally, factoring out an e to the x, we get e to the x times cosine of x plus sine of x. The last example here is y is equal to sine of x over x. Here we would use the quotient rule. So that would be the denominator or bottom times the derivative of the top, which is derivative of sine of x, minus the top, which is sine of x, times the derivative of the bottom, which is derivative of x, which is just simply 1, divided by the denominator squared, which would be x squared. So since the derivative of sine of x is cosine of x, we get x cosine of x, and the derivative of x, of course, was 1, and we have just simply minus sine of x here. So here is the complete answer. Two more examples. The derivative of 5e to the x plus cosine of x. The derivative of e to the x is e to the x, so the derivative of 5e to the x is 5e to the x, and the derivative of cosine of x is minus sine of x. Now, using the product rule, we can find the derivative of sine of x times cosine of x. So that would be the first times the derivative of the second, which is derivative of cosine of x. Of course, that's minus sine of x, plus the second, which is cosine of x, times the derivative of the first, which is the derivative of sine of x. The derivative of sine of x is cosine of x. So multiplying all this out, you can see we'll put the positive term first. We'll get cosine squared of x minus sine squared of x. Now, one slightly more complicated example is given here, where you have to use the quotient rule. We want to calculate the derivative of cosine of x divided by 1 minus sine of x. So it is the denominator, or the bottom, which is 1 minus sine of x times the derivative of cosine of x, minus the top, which is minus cosine of x times the derivative of the denominator, or bottom, divided by the bottom squared, which is 1 minus sine of x quantity squared. d dx of cosine of x is, of course, minus sine of x. d dx of 1 minus sine of x is 0 minus cosine of x. So we now need to expand all this out, and we get minus sine of x plus sine squared of x, and this is plus cosine squared of x. And you will remember from pre-cal that sine squared plus cosine squared is 1, so we get 1 minus sine of x divided by 1 minus sine of x quantity squared. So factoring one of the factors out in each, in the numerator and denominator, we end up with 1 over 1 minus sine of x. Now the next example shows the motion of a weight with a spring on it, and I'm sure you've seen this happen before. If you have a weight on a spring and pull it from its rest position to a position below, stretch it out, and then let it go, it will begin to oscillate up and down, and the motion is governed by a cosine wave. So on the next page, we've got an equation S for the position of the body is 5 times cosine of t, and we're asked what are its velocity and acceleration at time t. Well, writing the position down, the velocity is the derivative of the position, which is derivative of 5 cosine of t, which is minus 5 sine of t. The acceleration is the derivative of the velocity. The derivative of sine is cosine of t, so we get minus 5 cosine of t for the acceleration function. And on the next page we have both of these graphs, and you see the position given by 5 cosine of t and the velocity given by minus 5 sine of t. Now to round this subsection out, we're going to look at the derivatives of several other trig functions. We will not prove each one of these, but we will prove the one for the derivative of the tangent of x, which will be secant squared of x. The derivative of cotangent of x, you'll see, is minus cosecant squared of x. The derivative of secant of x is secant of x tangent of x, and the derivative of cosecant of x is minus cosecant of x cotangent of x. And on the next page we're going to prove, using the quotient rule, the derivative of the tangent function. So the derivative of the tangent function, using an identity from pre-cal, the tangent is sine of x over cosine x, which is a nice quotient. Now we'll use a quotient rule to take the derivative. So using the quotient rule, it's the denominator, or the bottom time, which is cosine of x, times the derivative of the top, derivative of sine of x, minus the top, times the derivative of the bottom, which is the derivative of cosine of x, divided by the denominator squared, which is cosine squared of x. The derivative of sine of x is cosine of x. Derivative of cosine of x is minus sine. Multiplying this out, we get cosine squared x plus sine squared of x, which this is equal to 1. So we get 1 over cosine squared of x. But you remember 1 over cosine of x is equal to secant of x. So 1 over cosine squared of x would be secant squared of x. So that proves that the derivative of the tangent of x is secant squared of x. Now, we're going to find the second derivative of the function y equals secant of x. The first derivative of secant of x we were given on a previous slide. The derivative of secant of x is secant of x tangent of x. So to find the second derivative, we take the derivative of a product secant of x tangent of x. Well, that's going to be the first, which is secant of x times the derivative of tangent, plus the second, which is tangent of x, times the derivative of the first, which is the derivative of secant. The derivative of tangent is secant squared. The derivative of secant is secant of x tangent of x. Multiplying this out, we get secant cube of x plus secant of x tangent squared of x. And that is it.